Okay, so I'm going to talk you through waves in a pipe, and this is going to be the AS2 January 13. So the first question is saying that a loudspeaker is connected to a signal generator, and the signal generator and loudspeaker are placed towards the open end of the resonance tube. And it said the first two positions of resonance are obtained. Now obviously if it's to do with sound, so this here could be my resonance tube. This is the end of the resonance tube. So what's happening is, let's pretend this is a loudspeaker, okay, and the sound wave travels down through the resonance tube. It hits the bottom, or in the experiment it's where the sound wave hits the water, okay, so and the wave is then reflected back up. So at the bottom of the resonance tube, or where the resonance tube hits the water, we have a node. If we're going to hear a loud sound, it's going to mean that there is an antinode at the top of the resonance tube. So if we just look at a wave, so I'm going to draw a wave here, and we know it starts at a node and it ends on an antinode. So my antinode is here. So if that whole thing there is one wavelength, the distance from our first node to our first antinode is a quarter of a wavelength. So my first position of resonance that I'm going to draw for the January 13 for part B, part 1 paper is a quarter of a wave. So it is just that bit that goes up, and we're also going to draw on the reflection, so it looks like that. When you're doing your diagrams, please try to make sure that it does look even, as in the antinodes are the same height. Okay, then it says there's another diagram, another resonance tube below, and you have to draw the second mode of vibration. So again, we start at the node because it's the sound wave's going to travel down, hit here and reflect back, and we're going to go to our next antinode. So there's our first antinode, here's our second antinode. So that is a 3/4 of a wave. 3/4 can fit in there. So I'm going to draw this. So I'm going to have okay, so there's my nodes, my antinodes, my node, and again my antinodes in order for me to hear the loud sound. So the first calculation we have to do, it says that the tube is 30 centimeters long. So this whole thing is 0.3 meters, and it says that the velocity of sound is 340 meters per second, and it wants us to calculate the frequencies of these two modes. So what we're going to do is we're obviously going to be using our V is equal to F lambda equation, except in this here they actually give us the length of the tube. Now in the first one, our length of tube, which I'm going to call L, is 0.3, and that gives me, we've set up here, a quarter of a wave. So L is 0.3, that is equal to a quarter of a wave. So if I want to find my wavelength, it is going to be when I L over a quarter. When I divide by a fraction, we flip it, so it means 4L is equal to my wavelength. Now again, remember it tells me that L is 0.3, so it's going to be 4 times 0.3, and that's going to give me my wavelength of 1.2 meters. Now that I have my wavelength and I have my velocity, because it tells me in the question, I'm going to rearrange the equation to find F. So F is equal to V over my wavelength, so it's 340 divided by 1.2, and that is going to give me 283 hertz.